Just to recap where we are, part one of the analysis of this engine was the bar graph analysis of compression variation, relative compression. We then added some detail to that by introducing the scope and looking at current variation during the cranking phases. We're now going to use the WPS. I've already got a device in cylinder 1, so we're actually going to run this engine in real time, less the spark plug in cylinder 1. I'm going to attach WPS to cylinder 1. Now, I'm not intending to introduce that poor compression. I think we've proven that part conclusively in what we've just done, but put the WPS in the cylinder, connect the BNC lead, and it's on the 4th channel. I've adjusted the colour to black from yellow. I find it's a stronger colour. Let me close the bleed device so there's no leakage. There's no one-way valve in this device, so we're seeing real-time pressure. Now, let's go back to this flip chart, please, just for a moment. When you use a compression gauge, you only see half of the evidence, the positive pressure above 1 bar. You do not see the pressure differential, pressure, not suction, not vacuum. You do not see the pressure down here. I've removed the one-way valve from the compression adapter, so we're going to see total pressure in the cylinder in real time when the engine runs. So WPS is connected. We are now going to select channel 4 and select the input as WPS, range 1, which allows us up to 35 bar. Switch the device on, range 1, no zoom. And I'm going to suggest that the 2 to 14 bar is more than enough, because one of the interesting things you'll notice, so we have now got a measurement range actually in pressure, and you'll notice that we have some very interesting results, because potentially the pressure in this engine will be, say, 10 bar, thereabouts. What you're going to see in actual fact, when the engine runs, the pressure is actually much less than that. So why is the pressure greater when you crank the engine and use a compression gauge than it is using WPS when the engine runs? Well, that's down to rotation speed. It has less time to draw air in, so less air is less compression. So you will not get the same result, but it's real time. Why do I want to focus on real time? And I'll tell you why. This goes back to this belief of mine about establishing the true position of the valves relative to the 4-stroke cycle. That on a modern engine, and this is a CDA engine, so it's a 1.8 CDA VAG engine, it has electronic control of the intake camshaft. That means that the computer has part control of when the intake valves open and close independently of the timing chain. Now, I've used that set of words very carefully. So you've got to ask the question, as a diagnostic assessment, you have to ask the question, what mechanical mechanism does the engine you're assessing have that will affect your results electronically? Now, Audi are in a position now where in some engines you have adjustment of both camshafts, inlet and exhaust, and with Audi valve lift, where the actual lift of the valve is altered electronically. So it is not just the timing chain that dictates where the camshafts are in relation to the piston, but very much the computer. And that's the bit I have a problem with. So we're going to do something very interesting in the next series of tests. We're going to add the lot together. So initially, we're now going to add compression on top of the cranking result. So I think we're set up. We're ready to go. We've got pressure set. We've still got voltage, still got current. Let's now run the engine. So I just need to push the loom back into the coils. It will run on 3 cylinders, and then we'll analyse the results. So we'll enable the engine to run, less one cylinder. So, how does this help us evaluate what's happening inside the engine? Well, let's just see what sort of information we've got. Let's go back to the first page and have a look at compression. Let's just shrink that box. Now you notice that during the cranking phase, here we can see the current being consumed by the starter motor against compression. And you can see that compression during the cranking phase is around 7 bar of pressure, 7 atmospheres. Doesn't sound healthy, but look how it drops off once the engine starts. We get quite a dramatic change. Let me just exit that page, go to the next page and look at stable idle. Let's have a look at the pressure in the cylinder here. 1.7 bar. It's a truthful figure. It's accurate. The throttle is closed, of course, so that's going to inhibit the ability of the engine to draw air in, yes. Less volume, less pressure. So, of course, when you do a compression test, your throttle is normally wide open. This engine's at idle. So, you're not going to get the same compression. So, how can we then analyse the results? Well, first of all, we only need to look at a couple of events. So let's pick, if you like, 2 or 3 compression events. We're just looking at one cylinder event now. Now we now need to overlay on top of this the theoretical position of the engine. So let's ask for 4 cursors. So we're now going to convert pressure into an angular relationship. So we're dividing time by the rotation events of the 4-stroke cycle. We can appreciate that 2 revolutions of the engine produces the 4 strokes. And we can now even zoom into that. And now we can see, let's just move this little box out of the way. We can now see the events that take place. Now, I want to put 2 more cursors, 2 very important cursors now on here. That goes back to this discussion I had about pressure. Let's make the first cursor absolute 0. Now the scope is suggesting it's -1 bar. It isn't -1 bar, it's 0. No, pretty accurately there. So I've set the cursor at absolute 0. The second cursor I'm going to set at +1 bar, which is actually going to give us, there we go, that's fairly accurate. So absolute 0 and 1 atmosphere. Now we can understand the difference, pressure differential in the positive zone during compression events or events where pressure is greater than atmosphere. Atmosphere is now here. And these events, which take place still at a pressure but is below that of atmosphere. So let me explain my take on this image. The very easy one is that this is the compression event, and the first thing you should look for is that symmetry, a symmetrical image both on compression. As the piston moves up, obviously the piston is moving up the bore at this point here to a peak which is obviously TDC, the highest point of the piston in the cylinder, at which point fuel and air will have been added and ignition will take place. And once the air and fuel ignites, it burns, it creates an expansion of pressure, and it pushes the piston back down, so it builds up a positive pressure, pushing the piston back down the bore, producing the power that the vehicle requires from the engine. Well, I have an interesting question. If this is the power stroke, and it definitely is, why is the pressure dropped below that of atmosphere? Now, it's called an expansion void, and it's a void established during the expansion that takes place in the cylinder. Now, the principles of this are laid down by Boyles' law, and it's the properties of gases under pressure. Now, in our case, what we have is a sealed chamber, and I hope that the valves are closed. I hope they're not leaking, because all of this will be affected both by engine speed and by camshaft timing. I hope I've made that clear. The computer now has some take on this as well, but certainly on the power stroke, those valves are closed. The piston is being pushed down by the expanding gases. Now, Boyle's law lays down the principle that if the volume expands in a sealed environment, the cylinder, you will reduce the pressure. And the more efficient the expansion is within that sealed chamber, the greater the expansion will be. So this actually reflects on the efficiency of the seal in the cylinder as the piston falls or is actually being pushed down. So that is an efficiency statement, if you like, during the power stroke, and it should more or less equal this zone here. Well, this is the intake event, if you like. We'll come to that in a moment. So, okay, we can see that we have quite a healthy period. We'll take some measurements of that, because normally if you were to use a gauge, I'm going to call it a vacuum gauge, we normally use a vacuum gauge and we measure these events with a vacuum gauge, and we would expect, and the lower the reading, the more healthy. There's absolute zero. We're never going to meet absolute zero. That's 1,000 millibar, that's absolute zero. We expect around 300 millibar, thereabouts. Obviously, that's 1,000, half is 500. It's looking healthy, but we'll measure it afterwards and get an actual figure for this period here. So, what's going to happen here? This is the bottom of the stroke. Now, if we're being picky, I'm just going to draw a little temporary box around there. Whoa! If that piston is still coming down, this is the bottom of the stroke, why has the pressure started to increase? Surely that's not possible. I've just made a statement that in an expansion of area, the pressure drops. Yes, it does. There's the proof. It's still a pressure. So why has it started to rise before the piston meets absolute bottom dead centre, before it comes up on the exhaust stroke? And the answer is the exhaust valve has opened. So we now can prove exactly when the exhaust valve has opened. So why has the pressure gone up? Pressure differential, because in the exhaust stream, the pressure will be higher than it is down here. Pressure differential, you're going to get flow. So it's actually going to draw in a little bit of exhaust gas at the bottom of that stroke. It has to. Pressure transfer. Then the piston starts to move back up the bore, up to TDC. TDC is here, 360 degrees. So how can we use this part? Well, this represents the pressures in the cylinder as the area reduces. So you're going to increase pressure, reduction in volume, increase in pressure. And you'll notice that it goes positive of atmosphere. I'm using these expressions quite carefully. So what does that represent? Well, it represents the pressure in the exhaust stream pushing the gases out of the exhaust system. And normally that would be somewhere around maximum of 3 psi, 3 psi? 150 millibar. It depends on the speed of the engine and the volume of gases, obviously. But there's a very minimal amount of pressure in the exhaust stream at that point. Had the exhaust been blocked, or let's say the exhaust valve didn't open for whatever reason, then that pressure, of course, would increase dramatically, depending on how bad the blockage was. So, in effect, I can think back in years gone by when I've suspected a blocked exhaust, and I've dropped the exhaust pipe to run the engine to see if it's fixed the problem. Well, there's no need. There's your evidence. This exhaust is not blocked. Had it been blocked, that would have increased dramatically. Okay, so we've now gone slightly positive during the exhaust. Well, hang on a moment. The piston isn't at the top, so why is the pressure starting to drop below atmosphere again? Pressure differential. Something has happened here. There's a positive pressure in the exhaust stream. Gases are going into the exhaust, and suddenly it decides the pressure is going to drop again. Something's happened to cause this differential. Well, the only place you've got a differential is in the intake manifold with a closed throttle. So you've got a lower pressure. It's still a pressure, not a suction, not a vacuum. You have a lower pressure in the manifold, in the intake manifold, so the inlet valve must have opened at that point there to create this change, because there's TDC. Piston's not yet at the top. So we now know where the intake valve has opened. Why have they opened it so early? There's a very interesting reason now for this, and that is that this engine and some of its family members do not use an EGR valve, thank God. What they do is allow the incoming fresh air, clean air charge, which is this bit, to draw in it and contain some of the exhaust gases. So by opening the valve early, it actually retains about 10% of the exhaust gases to help NOx reduction without the use of EGR, which is, in my opinion, a really good idea. But this is variable. This has got a variable intake valve angle control under the influence of the ECU. And this is the problem I have. I know what's going on here. How do I know the valve timing is correct? Because I don't really know what the ECU is up to. I need to look at the serial data on the ECU map to understand what the opening position of the inlet valve is electronically, because it's going to affect this evaluation. So you can see I've got this little bit of a conflict here. We're going to do something perhaps that will help us assess that a little bit later on. So, intake stroke, clean air. The piston now is definitely on the way down here, drawing in the fresh air charge, which, assuming there isn't a blockage. Now, what would happen if the inlet valve didn't open, or there was a severe restriction on the intake system? This pressure is going to go even lower. You're going to get an unduly high intake pressure differential, and it's going to pull this pressure much lower than the 300 millibar we anticipate as being a good figure. Those two figures should more or less balance. There's a slight difference on that than there is on the intake stroke. Slight difference here. What's happened here? Well, I'm going to explain this as a feature of the camshaft control on the ECU. The pressure does start to increase. The valve is still open. The intake valve, I suspect, starts to close somewhere around here, at which point then the piston starts to move up, creating the compression tower, and the whole cycle starts again. So very much what happens here and down here is now very much part of the computer control of the intake valve timing. So that's my take. Also, you may wish to look at peak pressures, of course, and acceleration. We did accelerate the vehicle, and you can see under acceleration, the compression under acceleration has gone to just short of 7 bar, which was the same as it was at low engine speed cranking. Still not the same value you get with a compression gauge, because unfortunately, compression gauge lies to us. It's got a one-way valve in there. And also of great interest is the closed throttle high engine speed events, where you can see that compression now is very poor. We've not drawn the air in, so we can't compress it. So this would be the equivalent of an intake valve not opening. Don't pull air in, you can't compress it. The exhaust event here takes place. You can see there the reaction with the valve opening and closing. And we get a much superior suction. High engine speed, closed throttle, pressure differential now is much greater in this zone than it is there. We traditionally call this vacuum, and we would expect about 25 inches of mercury, thereabouts, minus 300 millibar, 0.75 of an atmosphere, below atmosphere. And we can measure it. Pull that down there. That's 227 millibar. Now I said 300 millibar is a good figure that you'd normally use on a gauge. We're 227 millibar, closed throttle, high engine speed. That is a good figure, proving that the cylinder is sealed during the intake stroke, because this is the intake stroke before compression. So we have a good cylinder. And you could say that that event there it's the same cylinder we're looking at, of course, so there's a slight difference with that event, but pretty much they're all of a much the same figure, and 227 millibar is a good induction figure, very healthy figure. So there we have my analysis of the compression done in real time. And why do I like the real time part of it? Because we have the correct rotation speed, not just cranking. We have oil pressure, because remember that the valve mechanism is controlled by oil, an actuator with a variator that controls the position of the cam. So the cam is in a real position. Temperature, heat, the engine is running. We have hydraulic lifters, so the lifters are being operated hydraulically as they should be, which will be entirely different if it was cranking. So basically, all of the assets which take place when the engine is running are now present. So for me, real-time compression is the only way to do it. I do not do crank-only compression testing anymore. Let's now go to the next phase of this presentation and look at the relationship of camshaft and crankshaft and see how this helps us to predict the physical position of the engine relevant to the four-stroke cycle, the Otto cycle.